Welcome to the Module 3.5 Shapes of Graphs notes. Our objective for today is that I can determine whether functions have line symmetry and, if so, find the line of symmetry. And I can identify extrema and where functions are increasing and decreasing, and I can determine end behaviors of graphs of functions. Now we have some new vocabulary words for today. The first one is line of symmetry. And this is going to be a line that you can draw on the graph where the left half of the figure matches the right half of the figure. Exactly, and that is the key. It has to exactly match. The axis of symmetry is a vertical line in the form of x is equal to a number. This is going to be the line that there is a reflection across. A relative min is the lowest nearby y value on the graph, and a relative max is the highest nearby y value on the graph. A root is any value that makes an equation true, and a zero is an intercept of the graph. All right, so we have an example over here with relative minimum and relative maximum shown. So you can see out of this left portion, point A is the lowest out of that. That's why it's relative. And point B is the highest given that part of the curve. Again, that's why we're saying it's relative. It's not the absolute minimum or maximum, it's a relative maximum. And this is particularly true when you have different movements in your shape. You're going to be looking at relative mins and maxes. So for examples A and B, we are given the fact that there is a line of symmetry here. And so in letter A, it's dashed in this kind of orange color. And we see that the left side is exactly the same as the right side as you look at it. So the equation that would represent that, we need to have x is equal to a number. So the number that x or that line is on is x equals 0, otherwise known as the y-axis. So this is symmetrical across the y-axis. As you look on the left side and the right side, you're going to the exact same places, to the left and to the right. Now, as we look at letter B, again, we have a shape that is symmetrical. We see a mirror from one side to the other. For example, we have a pointed one to the left of it and one to the right of it. And here we're two to the left and two to the right. So we're seeing that we're having the same function, the same shape on each side. And now we want to figure out where is this one equal. So we have x is equal to -1. That is where our vertical line stands. That is going to be our reflection point or our symmetry point. Now, letter C, we're told we need to determine whether there is a line of symmetry, and if so, write and draw it. Now, as I look at this, some of you might say, well, your line of symmetry is like here, because then you have one side matching the other. But we were told that a line of symmetry is, or an axis of symmetry is a vertical line. So if we were to draw a vertical line in on this graph, and if I grab it, is there anywhere that I can move that line and get the left side to match exactly what the right side is doing? The answer is no. So this is not symmetric. There is no symmetry. There's no line symmetry here. Now, letter D. I'm going to grab that line from the previous question. We're going to move that across. I'm looking for a point where the left side is going to match the right side, and I believe I found one right here. Right? I have this like M shape, and now it's symmetrical from the left side to the right side. If I look at this, we've got, oops, don't want to grab the line. I want it 1, 2, 3 boxes to the left, 1, 2, 3 boxes that way. So we have these being symmetrical, right? 1, 1, 2, 2. So we're seeing the same shape going on this graph. So yes, this is symmetrical, and I put my green line where it is already. X is going to be equal to 1.5. Now, letter E, we have a V-shaped graph. And if I look at this, I see a line of symmetry right there. And again, we could find some test points and see. We go 1 and 2 to the right, 1 and 2 on the left. 1, 2, 3, 4 on the right, 1, 2, 3, 4 on the left. So yes, this is symmetry, and we need to write in our line x is equal to 5. That's our vertical line that's going to go through that line, or that inflection point. Now, on the next page, we have 3 you-try problems. I would like you to try those 3 now on your own, and then let's check your work against mine. Letter F. Letter F, we do have a line of symmetry. And it's going to look like this. All right, so that's going to be x is equal to -1, -2. So x equals -2. Yes, this is symmetrical. Letter G, another one of these V-shaped graphs. This is an absolute value graph. So there is our equation, and we are at 1, 2, 3. X is equal to 3. Yes, there is an axis of symmetry here. Now, letter H, as I look at this one, is there anywhere that I could draw that line and have it become show a mirror on left and right side? Nope, definitely not. Nowhere on there. So this is not symmetrical. Now, if we look at letter A in example 2, interpret symmetry. A fountain is spraying a stream of water into the air. The solid portion of the graph represents the path of the water, where x is the distance in feet from the fountain and y is the height in feet of the stream. Find and interpret any symmetry in the graph of the function. So first, we're going to find our axis of symmetry. And if I look at it, I see a relative maximum there. So I have a line of symmetry. My line of symmetry is going to be x is equal to 2. And what do I know about this? Well, what's symmetrical? This part is going to match this part. So the height from 0 to 2 seconds is the same as from 2 to 4 seconds. Or sorry, 2 to 4 feet. Okay, not seconds. This is measured in feet. So our height on our left side is the same as the height on the right side for those portions. That is the part of the graph that is going to be symmetrical. All right, now take a look at letter B. That's a you-try problem. I want you to do that on your own and then check your work against mine. The solid portion of the graph represents the path of a golf ball after it is hit off of a platform, where x is the distance in feet the ball travels and y is the height in feet of the golf ball. Use the graph to describe any symmetry that you see. So I do see some symmetry here, and it's right about here. So this is going to be an approximation, and I'm going to say that that line is approximately at x is equal to 90. Now, the height from 0 to 90 feet is the same or is symmetrical to the height from 90 to 180 feet. So from here to here is going to be the same as from here to here. Those are going to be mimicking. This is a classic problem in Newtonian physics. This is a ballistics problem. Any kind of a falling object model, all of these things, anything that is subject to the forces of gravity is actually going to go on an arc like this. Now, where could this be useful? Well, if you're ever playing the game Angry Birds, you can use this kind of math and this kind of line symmetry to figure out exactly where your bird is going to land given the approach angle that you're taking. And so you could figure out how are you going to collide into other objects based on what you see of your parabola, your curve. Now, we're going to go on to question number 3, or example number 3. And it's going to be determine increasing and decreasing parts of a graph or a function. So when is it going to be increasing? Well, it's going to be increasing when we're going up. So it's increasing when x is greater than 0 for that graph. When is it going to be decreasing? It's this section right here. So that's going to be decreasing as we go from left to right. That's going to be when x is less than 0. Our trend line is going down. We're angled downwards at each of these points, right? If we think of the slope, we are angling downwards. We're going down until you get to the very bottom when you level out, and then you start going up again. Right? So as we're following the path, we're going down, 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 and then we start going up. Right? You can try letter B on your own. Determine where is it increasing and where is it decreasing as we move from left to right. All right, we are increasing in this red portion here. So increasing when x is less than 1. We are decreasing when x is greater than 1. All right. Example 4 is going to be all about determining the extrema of the graph of the function. Determine the extrema of f of x, and then identify each point as a relative maximum or a relative minimum. So our extrema on this is this point down here. It's this kind of off, out of the way of the rest of it. So that is our extreme point. It's our outside point. And that's our relative minimum. It's also an absolute minimum for this one, but it is, yeah. All right, so on letter B, we have more examples here. And we're looking for extrema, so we're looking for places that are at the edge of one type of graph, whether it's increasing or decreasing. These are inflection points, they're change points. So my extrema, my change points, are going to be B, right, because we're going from decreasing to increasing. It's going to be C, where we're going from increasing to decreasing again. And then letter D, where we're going from decreasing back to increasing. Those are extrema. They are places where we are making changes. Okay. Now, our mins, our relative min, is going to be letters B and D, right? Because those are our bottoms of our trough. That's the minimum. Our maximum is going to be at letter C. So in this case, we have 3 extrema. 2 of them are minimums. 1 of them are maximums. Now, letter C, again, one of these absolute value graphs, our extrema is going to be this point right here. And it is at the bottom, so it is a minimum. So it's a min. There are two you try problems that I would like you to do on your own. Go ahead and try them now. So for letter A, our extrema are going to be B and D. Those are our extremas. I am at a max at letter B, and I am at a min at letter C. And example B here, my extrema is at the top, and that is a maximum. All right, we're going to move on to example 5. Interpret extrema of the graph of the function. So a comic book store uses a function to model its profit in thousands of dollars given the price in dollars that it charges for individual issues. Determine whether point D is a relative minimum, relative maximum, or neither, and then interpret its meaning from the context of the situation. So if I look at the graph and zoom in on it, focused, right, we're looking at point D up at the top there. We're at the top of the graph, so this is a relative maximum. All right, that's a relative max. And now it also asked us, what is the meaning of it in the context of the situation? Well, what's being maximized? What are we at our highest of? We are at the highest, if we look at our scale on our y-axis, we have the highest earnings. So we have the most earnings when we are at point D. So to put it another way and be more specific, if we were to charge $4 per issue, we would equal, take that comma away, we're going to equal $80,000 in earnings. All right, so that's the maximum. You could charge more per comic book, but you're not going to be able to make as much money as if you charge $4 per issue. That is your magic number. This is literally market research. What is going to be the maximum profit? Where can I charge the most for an object or for a product that is going to get me the most profit? Because if you start charging too much, people aren't going to buy as much. If you're charging too little, you're not going to be able to cover your costs. So you're not making enough. You may sell a lot, but you're not going to be making enough money. All right, so let's look at our next example here. We have aerobatics, or stunt flying, is the practice of intentional maneuvers of an aircraft that are not necessary for normal flight. Lincoln Beachey is an inventor of aerobatics, and he was known for his stunt called the Dip of Death, in which his plane would plummet towards the ground from 5,000 feet until he leveled his plane. His distance from the ground during the stunt can be approximately modeled by the function f of x. Identify any extrema in the context. So point A is the one we're given. So point A is a relative maximum. And what does that tell us? It tells us that at 20 seconds, he was at 5,000 feet. The height was 5,000 feet. All right. That is our extrema there. And then he levels off. So there really isn't an extrema at the bottom there. It just kind of levels and stops going down, hopefully, if he doesn't crash. All right. Examples 6 and 7 are combined, and it's going to be determine end behaviors of graphs. So linear and nonlinear graphs. The thing we're looking for is the arrow at the end and what it's doing. So at the right end of graph A, as x increases, what's going to happen to y? Y decreases. And on the left side, as x decreases, y decreases. Sorry, the red one is wrong. As y increases, or as x increases, y increases. Right? Our x values are getting bigger, our y values are getting bigger as we move to the right. As we move to the left, they're both getting smaller. Now, letter B, again, we're following and focusing on the end of the graph. So on this end of the graph, as x increases, what's happening to our y values? They're continuing to go up. On the other side, as x decreases, what are we seeing happening? Our y values are decreasing as well. Okay. So letter C, right? We're following our pathway. As x increases, y is also going to increase. On our left side, as x decreases, as our x values get smaller, y increases as well. All right, so no matter what on this parabola, our y values are increasing no matter what we do with our x values. All right, turn to the last page. And there are two final U-try problems. Please go ahead and do those. So letter A, as, we'll start on our left side, as x decreases, our y values are going to increase. Right? As x gets further to the left, our y values are getting higher and higher. On the right side, as x increases, our y values also increase. All right, letter B. We have another line, a linear relationship. So as x increases, y also increases. A positive slope. On the other side, as x decreases, y also decreases. All right. Now, if you have any questions, please bring them to class. This marks the end of the Module 3 notes. Have a great day.